अस्सलामु अलैकुम। पिछले लेक्चर में हम बात कर रहे थे सॉफ्टवेयर डिज़ाइन क्वालिटी एट्रीब्यूट्स की। इस सिलसिला में हमने एब्स्ट्रैक्शन, रिफाइनमेंट और मॉड्यूलैरिटी की बात की थी। दैट वाज द 11th लेक्चर ऑन सॉफ्टवेयर क्वालिटी एश्योरेंस। नाउ वी आर discussing, we'll continue our discussion on the same topics, that is software quality assurance. Software quality assurance with respect to, as it relates to software design, is very important topic, because we had agreed in the last two lectures that software design is an important, rather a very important activity in which we have to inculcate or put in, so to speak, software quality. If we don't do that, if we don't aim for high software quality while the design process is underway, we do not expect to get high quality software design, and certainly not a high quality software application. So as I said, we will continue our discussion on quality attributes of software design. They are also known as design concepts. Without the application of or inclusion of these design concepts into our design process as well as into the design model, we don't expect the quality of software design to be to improve. So today we will continue our discussion on this topic. We will first discuss some design concepts, then we'll also discuss characteristics of some design methods. Without going into the specific details of any of the methods, we will see what characteristics these design methods provide us to enable one of them to be selected for our design approach. Previously, we had talked about abstraction, we had talked about refinement, and we had talked about modularity. Now, we are going to start our discussion with information hiding. You have to remember this thing, that all these design concepts are related to one another. Modules should be specified and designed so that information, which consists of both procedures as well as data, so the information contained within a module is accessible to only those modules which need that information. So this concept of need to know applies directly with information hiding. Another way to put it is that information which consists of data and procedures should be inaccessible to those modules which don't need this. This is a very important and fundamental concept in software design. So what this leads to is the decomposition of software design into modules which are independent in their own way, which have their own little secrets. Those secrets can be data, those secrets can be algorithms, and we have lots of those modules in a design, in a software system, and they communicate with each other in only those aspects where there is a need to know. So this is the compelling argument for communication. What this helps us is it reduces information flow, that is unnecessary information flow within different components, and it reduces the communication overhead that otherwise would be difficult to manage, because communication overhead can sometimes bog down the performance of the software application. If we look at information hiding and have a little bit of comparison with abstraction, we can say that abstraction helps to define the procedural or informational entities that make up the software. So abstraction helps in the procedural or informational entities that make up the software. On the other hand, information hiding defines the access constraints to both the procedural and informational entities. So information hiding constrains the access to entity which can be a function or which can be a class. That's what's meant by procedural or informational entities. It also encourages the use of local data structures within these entities, and so the other positive side effect that happens with the application of information hiding concept is that the changes are limited to only that entity, or possibly few other entities which this particular entity communicates with. There have been design methodologies based on the concept of information hiding. The Naval Research Lab software cost reduction design methodology was primarily based on the concept of information hiding. And later on, the object-oriented design philosophy also contains information hiding as one of its main blocks on which the object technology is built. Because even when you study object-oriented technology carefully, it has divided the data structures into primarily two types: private data or private data structures and public data and public data structures. And you can access these information, both algorithmic, that's procedural detail, as well as data, only through specified interfaces, and you cannot change them directly. That is the concept of information hiding. You have only access to those things which you need them, and that too by asking an explicit question, that is by calling a function or a procedure. The greatest benefits of information hiding are achieved when modifications are requested, especially during testing. As we have discussed, that modifications and changes will continue to be made by the customer or even by the developers. So the benefits of information hiding are fully realized when we are in the process of testing the software, or even after when we are in the maintenance. How is that achieved, or how is those benefits realized? Is by the same concept that I just described earlier. That is, the changes made in the modules would have a limited scope. There we would have eliminated the ripple effect that otherwise would have been unavoidable if the concept of information hiding has not been applied. And so the concept of information hiding forces us to localize data structures, to localize algorithmic information. And any information that a module would have to provide would have to be requested, and explicitly requested by an operation, and would be returned explicitly. This is a very important design concept which results in the high quality software designs. And as I have said, that both the Naval Research Lab software cost reduction methodology as well as the object-oriented paradigm and object-oriented design have both their roots in this concept of information hiding. This is a very important quality attribute as far as software designs are concerned. There was a time in our profession when the use of global variables and common blocks was very prevalent, and that resulted in so many problems at the execution time that research was done in order for us to have better ways to designing software. And information hiding is one such important concept that can substantially improve the quality of the software design. Let's now discuss the concept of cohesion. This word has been discussed or described at least earlier in this course, and I am positive that you have heard this concept earlier in your education or in your professional lives. Cohesion is the qualitative indication of the degree to which a module focuses on just one thing. Now, this may be a terse mathematical looking definition, but I'll explain it to you in very simple words. And that is that cohesion is a measure of the relative functional strength of a module. How strong a function, how strong a class, how strong a module is, that is what cohesion is. A cohesive module is focused on one thing. For example, if I'm using an object-oriented paradigm and I'm trying to model a class, I'm trying to develop a class which is an aircraft, then I should focus on the data structures and the operations that an aircraft does. And so it should be nothing more than an aircraft. I should not be doing operations which a bicycle would do, for example. Like wheeling is an operation which some people use with bicycles. Now, if I'm a very creative designer, I would say, okay, an aircraft should also be doing wheeling. But that's not a function of an aircraft. So if I'm using structure programming, or if I'm using object-oriented programming, or for any programming any programming technique for that matter, if the module that I'm developing is focused on one thing, if it's a object-oriented paradigm, it means a class. If it's a function or structure-oriented programming, then I can say that a function or a procedure is focused on one thing. If it's a function, it's doing one thing. If it's a class, it's based on the entity, the characteristics and the behaviors of that entity. The example that I just gave of an aircraft is an overkill to show you that some designers tend to include many different kinds of functionalities where they do not belong. And so the focus of attention on one thing while building a module is known as cohesion. Highly cohesive modules are best. They are better than mid-range cohesion, although we do accept in some cases mid-range cohesion, because mid-range cohesion is close to highly cohesive modules. But we do not accept in good designs low-end cohesion, because it is very bad. In that case, what would happen is that if you're modeling an entity, the data structures related to that entity would be split across in different entities. And so would be the case with functionality, that if you want to do one thing, that one thing or one result would be produced with the help of lots of computation going on in different modules or functions. So if you want to be a software designer, or if you want to be a software quality assurance expert, if you want to be a project manager, you want to be a task leader, technical leader, take this advice. Focus on developing highly cohesive modules. It does not matter which design methodology you are using. It does not matter which process model you are following. It does not matter which language you have selected. You must have highly cohesive modules. The definition of a module would then be affected by or impacted by the selection of the design method or design approach that you are taking. But cohesion is fundamental. I cannot emphasize more the importance of developing highly cohesive modules, highly cohesive components. There are a number of types of cohesion. There is coincidental cohesion that occurs when unrelated components of a system are bundled together. So coincidental cohesion relates to occurs when unrelated components of a system are bundled together. They don't have a relationship. Logical cohesion occurs when components performing similar functions are put together. For example, error handling is sometimes put together. Temporal cohesion occurs when components that are activated at a single time or time span are put together. So anything that happens at the same time or within a same time frame, those components or those modules would be categorized as having temporal cohesion or temporally cohesive. Procedural cohesion occurs when elements in a component form a single control sequence. So it has to do with the sequencing of events. Then we have the communicational cohesion. It occurs when all the elements of a component operate on the same input data, same output data, or operate on one or more areas of the data structure. Next is sequential cohesion, which occurs when output of one element becomes the input of the next element of another element. So this is another form of cohesion. Functional cohesion occurs when each part of a component is necessary for the execution of a single function. And this sort of cohesion is the one that I was talking about, where you are focused on one thing. And the last type of cohesion is object cohesion. It occurs when functions of a common class of objects are aggregated with the class. That is also known as, in object terminology, class functions. In this scheme, interfaces are designed in such a way that they reveal as little information as possible about the inner workings of the object. And this concept we have just discussed is captured by information hiding. So as I just said, that these design concepts relate to each other, and they complement and supplement each other, and together they make our designs very strong, and they end up in a design which is of high quality. Let's talk about yet another concept which is very important as far as the quality of software design is concerned, and that is coupling. Coupling is a qualitative indication of the degree to which a module is connected to other modules and to the outside world. Cohesiveness, as we had just concluded discussing, deals with the inner strength of the module. Coupling, on the other hand, deals with how much one module is connected with other modules. So we can also say that coupling is a measure of interconnection among modules in a software structure. If we have many interconnections, that is one situation. If we have no interconnections, that's an isolated system. And in some cases, we have a reasonable amount of interconnections. That's the desirable situations. So we can say that loose coupling is better. Simple connectivity is easier to understand and less prone to ripple effect. Remember, we have to reduce, ideally eliminate, but at least reduce to a certain degree the effect of changes that are going to always come in software projects. So the ripple effect these changes cause sometimes can be devastating on the both the project as well as on the product. So we have said that coupling is the interconnection of different modules, and we would like loose coupling. Let's now talk about different types of coupling. Indirect coupling occurs when one object interfaces with another object through a third component. So we have a third party communicating between two components. This is the most desirable form of coupling, or shall I say, this is the example of loose coupling, because two components are communicating with each other, yet they are not communicating directly. They are talking through a third party. Another form of indirect coupling occurs when using data-driven style of computation. Data coupling occurs, that's the second form of second type of coupling, when a portion of data structure is passed among modules. When using data coupling, shorter parameter lists are preferred to long parameter lists. This is not indirect coupling. This is direct coupling. We have one component or one element or one module communicating with another module. And we are passing data. What we are saying is that this is also an acceptable form of communication. We do have to send data from one module to another, but what we are saying is that we would like the data structure to be developed in such a way that the parameter lists are short, instead of sending, let's say, large number of variables to the other communicating element. Stamp coupling occurs when a portion of data structure is passed among modules. Again, you have a data structure that is being sent, not in the form of individual data elements, but in form of data structure. Here again, we prefer small number of actual arguments as compared to larger number of actual arguments, because only that data should be sent which is really needed. So I can say that there is a component A, there is a component B, and I'm sending an object of class C from A to B. Now it is not necessary that all the characteristics of object of class C are needed by component B. So I should only send those which are necessary. So there are techniques available. I can maybe inherit from class C and include only those things which are needed by B. So there are techniques available which can reduce the overhead of communication between when we are sending data. The next form of coupling is control coupling. Control coupling occurs when information is passed to a module that affects its internal control. Now this is bad. This is undesirable because it requires the calling module to know about the internal operations of the module being called. So this is a form which is not desirable in coupling. We understand that without having some coupling, there would be no system. Everything would be independent and standalone. That is not how the world works. That is now not how the software works. The conditions for software in this new century is interoperability. But that does not mean that one system or one software product or one software component or one software module has to know the internal details about the one that it is calling. And so that is totally against the concept of information hiding. So this is undesirable form of coupling. The reverse of this would be an external coupling. That occurs when a module is dependent on the external environment. So instead of a calling module knowing about the called module, here we have a module which requires lots of things or is dependent on the external environment. This is also tight coupling and an undesirable form of coupling. Results in software designs which are inflexible, which are not reusable, which can cause major redesign activity if changes are made, and changes will be made. And when we have rework, when we have redesign, the possibility of introducing new defects, cost overruns, schedule overruns, all the bad things with respect to quality assurance. The next type of coupling is common coupling. It occurs when modules access common areas of global or shared data. This can result, unintentionally though, but can result in the interference of operation of one module with another module. And a few minutes ago, I was just talking about this kind of thing, that when early days of computing, we had these enormous use of common blocks and global variables, and everyone liked it. And then suddenly they realized that this is causing major problem to quality of our data, integrity of the data, and quality of our software designs. So as a result, research was done to come up with these quality concepts, quality design concepts that we are discussing here today. Then we have content coupling. Content coupling occurs when one module uses information contained in another module. Now this is also a form of tight coupling. If a module requests through an interface and asks for a service, and that service is provided, this is an indication of tight coupling between two modules. It, however, is sometimes unavoidable, because these are how the components are integrated together. This ends the discussion on coupling, and also on the quality design concepts. However, let me just summarize them again. We had discussed abstraction, refinement, modularity in the last lecture. Today we have discussed information hiding, cohesion, and coupling. These 6 are the fundamental design concepts. They will result in high quality software designs and ultimately high quality software products. As I said before when I was discussing cohesion, if you want to be a good designer, and you want to be a good programmer, you want to be a good SQA person, learn these concepts. These are concepts which should be like ingrained in your brain. They should become your second habit. They should become natural to you. So read about them, practice them, learn them through studying existing designs. When you create designs, apply them, improve them in the next try. And once you master them, I assure you that your designs will get better and better quality-wise, and stable and stable. These designs cross-cut the methodologies, they cross-cut the process models. They are like the kernel. Remember, we started our discussion on the concept of the importance of design, that it sits as a kernel in software engineering. There are a number of other design concepts which I will briefly mention for you for sake of completeness. But all of these are also related to the 6 fundamental that we had discussed just now. They are the emphasis on software architecture. It gives you a skeleton of the software solution. Then you have control hierarchy of how you would break your tasks. Structured partitioning is directly related to module development and module partitioning. Then you have emphasis on data structures. Data structures again are a very important concept. As a designer, it is your responsibility to pick the data structure which makes sense for that kind of data. With this new advances in computing technology, sometimes new students or naive professionals don't give proper care to this. But data structures is fundamental. If you have an integer, if you are passing an integer, for example, you have multiple options available in the language of your choice. But you should choose the one that makes most sense for that class of inputs. Remember, we talked about classes of inputs and classes of outputs, and that is what it is, that an integer has to be stored, but what is the range of possible inputs? And here you should also allow that concept of gentle degradation that we talked about when we were having generic discussion on software design. So 6 concepts that we have talked about: data structures, good grooming, good grounding in data structures, good thinking about data structures is going to help you make a very good software designer, a designer who develops high quality software designs. Remember, every discussion, every point that we talk about is related to quality assurance. We have high quality software designs, we have fewer defects in our designs, we have a high quality product at the end. Customer is happy. Then we have functional independence, which is related to modularity, which is related to cohesion. Then we have encapsulation, which is related to information hiding. Then we have inheritance, polymorphism. These two are available in object-oriented languages or object-oriented designs only. Very valuable concepts, but since they are not generic enough to be included for all design approaches, there is no point in discussing them here. But you must remember the 6 that we have discussed in detail, and then we had emphasis on developing good data structures. You follow the design principles for the design process as well as for the design model. You continuously apply the guidelines to evaluate your design process as well as your design model, and good knowledge about the application domain, and at the end you have high quality software design. But only if you're committed to developing one. So as a professional, as a student in software engineering, raise your bars for high quality. Set personal goals that you will not accept low quality. You will not produce low quality work products. Once that is done, I have every confidence in you that you will produce high quality software design. However, I will also give you a word of advice at this time, and that is that you have to adopt a core set of ideas for each system design, because those ideas will then improve the conceptual integrity of the software design. And these 6 design concepts that we have just concluded discussing are that fundamental set of ideas. Focus on cohesion, focus on information hiding, focus on abstraction, perform stepwise refinement, develop good modules which are loosely coupled, and on the internal side of these, develop good data structures. Remember, you have requirements which are primarily of 2 types. These are stable requirements, things which are not going to change or are going to change very seldom. Then you have volatile requirements, things that are going to change frequently, or at least change sometimes. These are volatile requirements, and sometimes the rate of change also have to be monitored. Now, if you have these 2 kinds of requirements, your designs must incorporate these 2 things. Things which are modeled in such a way that incorporate stable requirements, and then you make the design in such a way that if changes are made, and they will be made, then the effect will be minimized, and as a result you will have a very high quality software design. Let's talk about a little bit on different design methods, or design methods in general. You have to use a design method which is most suitable for the problem at hand. You cannot just continue to apply one method that you have learned. That doesn't work. You don't have to use the latest method or the most popular design method. As a designer, you have to use your analytic thought and your analytic decision-making capabilities to select the design method that makes sense for this particular project. Remember, I described to you a statement by Michael Jackson that you have to think the right way. You have to get the right approach. That is your job as a designer. There are many structured design and object-oriented design methods to choose from. There's no dearth of them. There are so many of them available. What you need to do is to follow the design method's representation scheme. It helps you understand the design that you are creating, and it helps you to communicate the same to your team members, to your developers, to your customers if they are technical people. Now let's look at the characteristics of design methods. Design methods provide a mechanism for the translation of analysis model into design model or design representation. So there's a sequence of steps that you have to follow, and then you will end up in a design. Not without a lot of effort, not without this design application of the design concepts, but what design methods do is they provide you with the necessary thing, and that is uniformity and integrity of the design process. You're going to use the same graphical notation. You're going to use a circle in the same way or a bubble in the same way throughout. You're going to use a line or an arrow in the same way. And that provides you the mechanism that is important, that you don't create possibility of multiple interpretations in your design. A design method also provides you a notation for representation of functional components and their interfaces, which can then be used to implement them faithfully using a computer language. Design methods also provide you the heuristics for refinement and partitioning. So one of the fundamental concepts that we talked about in design was refinement. And these steps, these methodologies, these design methods provide you the guidance on how to refine your design and how to partition them in from different perspectives. Remember, we talked about the concept of viewing a design from multiple perspectives. These methods allow you to do partitioning in that way. And these methods also provide you guidelines for quality assessment. So see, everything that we do in design has to be assessed for quality, and every activity we do in design ends up in relationship with software quality. Now let's look at 5 concepts. These are the effective modularity criteria for design methods. We have talked about modularity in software design, but let's now talk about these criteria, and if these criteria are available in the design methods, then that method, when applied faithfully, can result in creating good modules for the software design model. These 5 criteria are: number 1, modular decomposability; number 2, modular composability; number 3, modular understanding; number 4, modular continuity; and number 5, modular protection. What we are saying here is that if a design method has these 5 things, or it can help you in dealing with these 5 concepts, then the modules that you will develop will result in a high quality software design. Remember, modularity is fundamental. Cohesion, coupling, information hiding, refinement, and abstraction are all related to modularity. So let's now discuss each one of them. Modular decomposability means that if a design method provides a systematic mechanism for decomposing the problems into subproblems, it will reduce the complexity of the overall problem. So what you're doing is your method is helping you to apply what abstraction to the problem, and you are dealing with abstraction and refinement here, that at higher level of problem you have abstraction, and then you are dealing with lower level of abstraction, and so you are decomposing the problem into sub-problems. So both abstraction and refinement are at work. The next is modular composability. That is, if a design method enables existing design concepts design components to be assembled into a new system. It will yield a modular solution that does not reinvent wheel. So let's say you have lots of components, so they are all at the most refined level, and then you combine some of them to add some abstraction. So it's like a reverse process. And if a method allows you to combine or compose larger systems out of an existing set of small components, then this allows you to follow that design principle, that the design should not reinvent the wheel. See, everything is coming together. Then you have modular understandability. That is, if a module can be understood as a stand-alone unit without reference to other modules, it will be easier to build and easier to change. Cohesion, concept of cohesion is being applied. You have a module which is focused on one thing. Then you have modular continuity. If small changes to a system requirement results in changes to individual modules rather than system-wide changes, the impact of change-induced side effects will be minimized. That is, the principle of coupling is being applied, that if the changes are resulting in minimal changes, either no changes to neighboring components or neighboring modules, or limited changes, then your design is promoting what is known as modular continuity. Last, we have modular protection. That is, if an aberrant condition occurs with a module and its effects are constrained within that module, the impact of error-induced side effects will be minimized. That is the concept that we talked about, that the design should handle aberrant data, events, and operational conditions in a gentle way and limit the damage that has to be done. Now, this concludes our discussion on software design as it relates to software quality assurance. In the last three lectures, we have talked about different aspects of software design as they related to quality assurance. In the last three lectures, I have equated the importance of design with high quality software. Emphasis on good design leads to high quality design, which leads to high quality software. So if you want to develop or be associated with high quality software products or services, put your money where it is most useful, and that is develop high quality designs. So I see you in the next lecture with another interesting topic. Bye.